Okay, hello and welcome to AIAIART, this somewhat experimental course that we're doing. Unfortunately, I recorded the first half of the first lesson, but not the second half. So this is going to be a retake without the benefit of interaction. It's just going to be me running through the material at a slightly faster pace for those who couldn't make the lesson. And apologies for this. In the future, I'm going to try and record the lesson so that we don't have to do this awkward, just me talking to myself. But anyway, I'm glad to have you with us. Let's start with quick introductions. So my name is Jonathan, or Jono. I am a data scientist, but that was my primary profession for several years, both working as a consultant and teaching the occasional course. More recently, just branched out into helping run a couple of other courses. I really enjoy teaching and experimenting with deep learning. And then even more recently than that, I've sort of branched into making art with AI. Part of a sort of sabbatical year that I'm taking and something that I'm really enjoying. So yeah, this course came about. We sort of realized that there was a bit of a gap. There's all these exciting tools coming out, but a lot of people who were using them felt like they didn't quite have the background or understanding to peek under the hood and start modifying and adapting these tools. So this course aims to change that. We're going to look at some of the tools that exist, right? How to do text to image generation, how to mess around with style transfer and so on. But more than that, we're going to try and get to a stage where we can really understand code when we go read through what other people have done. We can dig in and see exactly what is happening under the hood and why it works, and also look at ways that we can get more control over the outputs. So that's the goal. At least we're going to start from the basics, working with tensors and images in PyTorch. What is an optimization loop? What is gradient descent? Moving up through different generative networks, different architectures, looking at CLIP and how that's trained and how that works, taking it further, debugging tips, so on and so forth. So the way these lessons are going to be structured, we're going to have 4 main lessons, possibly some extra bonus content as time goes on, but 4 main lessons. So this is lesson 1. Each one is going to be this sort of big monolithic notebook, and that's what we're going to be sort of working through, and that's what I'll be leading you through today as well. So you can have this video sort of running off to the side. During the lesson, what we did is everyone just made their own copy of the notebook, so file, save a copy in Drive. That gives you something that you can modify and mess with and annotate without worrying about losing those changes. So I highly encourage you to grab the link from the Discord, follow along as we go, run the cells as I run them, try your own different outputs. I'll do some pauses for exercises, but you can also just pause the video to go back, dig in deeper if you don't understand something. So let's get started. We're going to run, if you haven't explored a Jupyter notebook before, Google Colab is basically just a notebook hosted on their machine. So once you connect, they're going to sort of give you this interface running on some machine in the cloud, the Google Compute Engine backend. And this is going to be some text and some code cells. It's really nice. It means we can hopefully mix in kind of explanation and documentation along with our code, so-called literate programming. So really great for like exploring concepts, testing things out. And if we execute Python code here, we can run it with the little play button, or we can hit Shift Enter to run the cell. This is going to run that code on the machine that's there and give us back the output. I sometimes hide the code away, but you can always click Show Code to see what's happening. In this case, just importing a few libraries. And again, when it's hidden like that, you can just run it on the side or hit Shift Enter. This is going to be the sort of consistent environment that we all share so that we don't have to worry about different library versions and getting things running locally. It's also nice because it gives us access to, if we need it, a GPU. So at the moment we're running with no hardware acceleration, but you can change that to GPU if you so desire, and for later lessons we'll be leaning heavily on that. Okay, don't watch the welcome video. This is pretty much the same content, and I've decided going forward I'll probably just record the lectures rather than creating these shorter videos, just because it's kind of a bit overwhelming to try and do that video production. I'd rather just do really nice text and explanations, and then have the live lecture be the video component. Okay, so like I said, we're cramming a lot into each of these big notebooks. There's 1 notebook per lesson, but a lot of this is going to be like illustrative examples. It's going to be small sort of atomic sections that you can dive into and explore, but also come back and reference later. So don't feel like you have to memorize everything, by no means. rather just just get the high-level overview, the concepts, and you can always come back for the specifics. So section 1, PyTorch and tensors. What is a tensor? We talked about various different ways of viewing this in the lesson, but basically we can think of this as some sort of structure or object that needs to encapsulate a set of numbers, right? And this could be a single number, this could be a vector of several numbers, this could be a matrix. And so I think the best sort of way of viewing tensors, depending on your background, might be to just think of them as multidimensional matrices or arrays of numbers, right? So all of these three here could be represented as tensors, and this is going to be what we're going to use as our sort of core data type. So we're going to be doing all of this in PyTorch. PyTorch is a library designed for deep learning, so it's designed to make creating neural networks, deep neural networks, and training them really easy. And a big chunk of that is just enabling a lot of tensor operations and doing all sorts of great additional things behind the scenes, which we'll talk about once we come to automatic differentiation and gradient descent. Okay, so the first section is going to look at some ways of creating tensors. We can create them from existing sort of data structures. We can create, there's a few sort of constructors that we can use, creating random tensors, creating tensors of a certain shape, similar to another tensor, creating sequences, and so on. So in the notebook, we're going to see there's a whole sort of series of examples, how to create tensors, how to manipulate them, what does it mean when we say, let's add this tensor and this tensor, how are we going to calculate that result? Reshaping, indexing, flipping, permuting, squeezing, etc. All of this terminology we're going to see by example exactly how that works. So let's dive into the notebook and start running it. And then I'll move quite quickly through these examples, and you're welcome to, like I said, pause the video if there's something you don't understand and spend some time sort of investigating. And I'll also try here in this sort of scratchpad notebook, I'll try and add some examples of how you might explore something a bit more deeply. Okay, so our very first operations, creating some tensors. Here we're passing in a list or a tuple of tuples, an NumPy array, and we can see the outputs here, pretty much what we would expect looking at the input. Just now the type is going to be type torch.tensor. So if we type A, we're going to see this is a torch tensor, and this is going to give us some methods and attributes specific to that. Okay, we can also use some constructors to make tensors, and I'd encourage you to, whenever you see something like this, change some of these parameters and examine how that affects the output. So we went from 5 to 4, and we saw that instead of 5 rows, we now have 4 rows of ones, each of which has sort of 3 elements. And so when we're using these constructors, the arguments that we pass in are the sizes of the different dimensions. So we'll use words like dimension, rank, size, shape, etc. But it's always to do with the sort of overall structure of this tensor. This is 4 rows, 3 columns. This one here is just 2 numbers. This one here is 1 tensor of 5 elements. Inside, it has these sort of Singleton dimensions, which we can look at. And you can always go and mess around with these. What happens if I do 2, 2? One of the questions we had in the lesson was, is there a limit, to some number of dimensions? No. You can mess with this as much as you like, and you'll see that the resultant shape is what you would expect. And if you're ever unsure, one of the most common things to do when you're debugging tensor operations is to just check the shape. Let's check the dimensions of this tensor. This is a 2 by 2 by 2 by 2 tensor, and we can access that with .shape. Okay, a few more constructors, torch.rand and torch.randn. There's a little question here, what is the difference? An easy way to explore this is to just plot a histogram, because this is creating random numbers. So if we create 100 random numbers using the randn function, we can then plot that distribution and see what range those numbers take. And here they're sort of centered around 0, standard deviation of about 1, but you can see it goes somewhat negative to somewhat positive. Whereas if we just did torch.rand, and let's up this to 1000, we can see this is now a more uniform distribution, and it's limited to 0 and 1. So those are going to be useful in different contexts. You can chop and change, and as always, you can just, if you need to know what's going on under the hood, if you type a question mark torch.rand, you can always look at the docstring and sort of function parameters, and see exactly what that function does and what it returns and what arguments it takes and so on. So useful little tip there. Okay, and then finally I think constructing tensors with the same shape as another tensor. So if 0 is like A, is going to make a tensor filled with zeros, the same shape as the tensor A that we created before. And then if we want to make sequences, torch.arange, torch.linspace. If you're familiar with NumPy, these methods work exactly the same. If not, you can see what they do here. We have this tensor 0 through 9, so up to but not including the end, moving with this step in between. Yeah, so pretty useful for creating tensors. What can we do with them? There's a little exercise here, by the way, to check your knowledge. Okay, so once we've made some tensors, we can operate on them in different ways. So we can use the methods built into PyTorch, torch.add, torch.multiply, and so on. But we can just as easily use these standard Python operators because many of the common operators have been overwritten such that they now work on tensors. But specifically they work as element-wise operations. So let's run this cell and then let's look at the output and try and understand exactly what that means. So we have two tensors here, x and y. What would it mean for us to add them? And so the answer, if you look at the output here, you can see it's the same via torch.add or just using the plus sign, is taking element by element. 1 plus 1 gives us 2. 2 plus 2 gives us 4. 4 plus 3 gives us 7. 8 plus 4 gives us 12. So it's not working on any sort of operation on the whole tensor. It's going element by element and matching them up. Likewise, if we did something like x times 2, we would see that this is now going to go, and it's smart enough to say, okay, I'm going to apply this operation to every element. 1 times 2, 2 times 2, 4 times 2, 8 times 2. So this is what we mean by element-wise, and you've got to be careful if you're expecting a matrix operation. You need to make sure that you use the appropriate matrix operation and not the default element-wise operation. But often we'll want to use this, and so this might behave just as you expect, in which case, perfect. Okay, so there's also some built-in methods for like aggregating or manipulating tensors. The examples here is using .sum to take this input tensor, so we can see the tensor x, and then sum the columns, sum the rows, and it's a little bit confusing here if you think too hard about it, what this axis or dimension argument is doing. Highly recommend, changing some of these dimensions, working it out for yourself, and seeing, okay, if we're saying the sum of the columns, so summing the columns here, we expect to get three values, right? This column, and this column, and that's what we do get when we specify axis is equal to 0. So you might be thinking, okay, isn't the 0th axis or 0th dimension the rows, and then the first dimension is the columns? Yeah, you've got to just sort of have a think, have a play, do some examples, and kind of get that set in your head why this appears to be flipped. And it helps to think which sort of axis are we moving across when we're summing. So anyway, you can try that out, do the same thing with the mean, get a feel for what the different shapes are, print out, okay, what is x.sum.shape, see what happens. Okay, so we said most operations are element-wise. There is matrix multiplication with the @ symbol, dot product with torch.dot. We might come across those later in the course, but for now, let's just move straight on ahead. What else can we do? Often we want to just access part of a tensor rather than operating on the whole tensor. So we can index in, and if you've done anything like working with NumPy, again, this should be fairly familiar. If not, spend a little bit of time to understand. So this tensor x here contains the numbers 0 through 9, up to but not including 10. So we can access just the last element, and we get 9. We can access just the first element with x0. If you're coming from a language like R, it might be x1, so you need to watch out for that. And then if we use this slice notation, you can read this as from 1 up to but not including 3, right? This is index 0, this is index 1, this is index 2, this is index 3. So when we say 1 up to 3, we're saying starting from here, including here, but not including the final one. Likewise, x minus 2 is going to be the number 8, right? And so when we say up to but not including minus 2, we're saying everything up to but not including that element and the ones after it. So again, can sometimes take a little bit of time to get used to. You can do a bit of practice if you'd like. But this is just us taking subsets, and this works just as well for multi-dimensional tensors, because we can say I want the first element in the first dimension, and then I want, looking now in the columns, the third up to but not including the fifth, and then a third dimension and a fourth dimension, and so on. So long as the tensor actually has those dimensions. Great, we can also reshape tensors, rearrange them, as long as the total number of elements doesn't change, right? You can't reshape a 3x4 tensor into an 8x2 tensor because you're going from 12 elements to 16 elements, and that just doesn't make sense. But we've got a little example here. We create a tensor using a range, so 0 up to but not including 12. We reshape it to be 6x2, then we flatten it out to be now this flattened version back to its original, as it were, reshape it to 3x4. And again, if you're ever wanting to check things, z.shape is going to tell us what the sort of final shape of this is. We're expecting 3x4, and that's what we see. So just make sure that you're familiar with working with reshaping. You can also transpose it, so z.t is going to rotate it 90 degrees, as it were. So you can see 0, 4, 8 was the first one in each row, there's another first in each column. And the shape is now going to be 4x3 instead of 3x4. We can stack tensors together using torch.cat, short for concatenate. So it's helpful here to maybe print out x and y, but let's just run the example and see. So actually let's do that. Print x, print y. So we've got two tensors here that we're just creating, x and y. We can stack them and specify dimension 0, and that's going to create this new tensor here. Or we can specify we want to stack them along the second dimension, and we're going to end up with this now. Instead of 6x4, we get a 3x8 tensor. And you can see this first sort of section here, 0, 1, 2, 3, 4, 5, 6, 7, that's x. This sort of right-hand half here is y. So again, can be slightly counterintuitive. You've got to think really carefully what dimension you want to stack things on. But when in doubt, try it out, and then check at the shape and see if that's what you expect. Final little step before we get to images. Sometimes we have singleton dimensions, right? A dimension where the size of that dimension is just 1. This can be because maybe we took the mean across some dimension, and now we just have a single one there, and we want to get rid of it, or we need to add one like that. Squeeze and unsqueeze are basically going to do exactly what we expect there. So here's an example to motivate this. X is a tensor 1x10, right? So if we try to access x0, we're getting the first element, but it's in the singleton dimension, so it's actually all 10 values. So if we wanted to get rid of that dimension, we could use x.squeeze, and we can see from shape 1x10, we've now just got shape 10, and accessing the first element gives us the first number, which is what we would want. If we want to go the opposite direction, unsqueeze to the rescue, and it takes an argument here to specify which dimension we'd like to, or whereabouts we'd like to add this extra dimension. So unsqueeze 0 is going to add it as the sort of first dimension. Unsqueeze 1 will plonk it right in the middle, so we have shape 5 by 1 by 5. We could use unsqueeze 2 or unsqueeze -1 to say add an extra dimension after the other dimensions. So useful functions, we'll see them in practice and we'll see why we use them. But for now, it's just nice to have, okay, if I ever need to come and check this out, I know in the first notebook we did tensor wrangling and there was a section on squeezing and unsqueezing. So you can come back here and find those bits of information. Okay, so let's move on to image operations then. How do we represent an image as a tensor? So we're going to be working with images a lot because we're making art. So first thing here, we're going to download PNG, the logo that I made for the course right at the beginning, when it suddenly became obvious that this was going to be a thing. So when we look at an image on a computer screen, each pixel of this image is going to be made up of some combination of red, green, and blue. And so the way the computers often represent these images behind the scenes is to have this big array where for each pixel we store the red value, the green value, the blue value, and then optionally some sort of transparency. And we can convert this image into an array. It's loaded with the Python imaging library, by the way. So from PIL import image just makes loading and saving files really easy. You can also use Torch's built-in functions to load images. But PIL is nice because, as you can see, it displays nicely in Jupyter. It gives us a sort of user-friendly way to interact with images. And we're going to work on how do we convert from this into like a PyTorch representation and back. But yeah, so if we convert this into a NumPy array first, we can see that it has 128 by 128 by 4, this big array. And this is going to be the width by the height by the number of channels. So we mentioned that sometimes it's an alpha channel, and in this case that's true. And we can plot this with matplotlib as well. I'm just showing this here as another example of a way we can view an image if we have it in this format. But we can also, since this is a NumPy array, we can convert it to a tensor with torch.tensor and then pass in the array, and we get what we might expect. We now have a tensor with shape 128 by 128 by 4. Right? And like I said, this is the width by the height by the number of channels. So this is what we would expect when working with the Python imaging library and matplotlib. But for a lot of PyTorch image operations, for various reasons, they expect it to be the number of channels first, as the first dimension, and then the width, and then the height. So we need to rearrange the order of our dimensions here, and the function that we're going to use to do that is the permute function. Right? So this little line of code here is saying, take the dimension that's index 2, so the third dimension, then the first dimension, and then the second dimension. And when we run this, we can see the shape is now 4 by 128 by 128, right? So we have our channels first, and this is going to be the preferred format for a lot of PyTorch stuff. Since we have the channels first, we can access each one individually. So just accessing channels first 0 is going to give us the first channel, channels first 1, the second channel, and so on. And you can see here we have the red, green, blue channels, and then the alpha channel is just all it's completely opaque. So in this image, there's nothing going on there. In others, you might see that there's some transparency that you would want to account for or use. Okay, final thing. I said PyTorch prefers to have the channels first, but actually they also generally expect to work with batches of images, that is multiple images at once. So your images are represented as a batch. So we have batch size by number of channels, by width, by height. And so when we've got just one image, we treat it like a batch of size 1, and we're going to use unsqueeze to create that. Little side note, we'll see that in operation once we get to the fun stuff in the bonus section. Okay, little coding exercise there. If you'd like to extract certain channels, practice squeeze and unsqueeze, practice converting back and forth with permute to go from the PIL format, which is width by height by channels, to PyTorch format and back again. But yeah, that's some sort of basics. I know I've moved through that quite quickly, so you're welcome to ask questions in the Slack channel, the Discord channel, if you're working through this in your own time and you encounter something that you're not sure about. I'm going to now move straight into section 2, but if you'd like to pause the video, get a cup of tea, we had a 10-minute break in the live lesson, just to let everything settle before we dive into part 2. Okay, part 2, gradient descent. So this is going to be a new concept, and we're going to try and understand it. So I started by looking up the Wikipedia definition, right, which says gradient descent is a first-order iterative optimization algorithm for finding a local minima of a differentiable function. The idea is to take repeated steps in the opposite direction of the gradient of the function at the current point, because this is the direction of steepest descent. And pretty much universally, this is the expression on everyone's face, what on earth is going on here? So we said, okay, we're going to break this down, we're going to do some examples, and we're going to try and understand. If you Google gradient descent, you're going to see lots and lots of pictures like this, which might give us this idea, okay, we're trying to move down some slope. There was a gif of someone skiing, but somehow we're trying to find some sort of minimum point. So let's dive into the notebook, let's work through this step by step, and let's see if we can fill in some gaps in that definition and our understanding. So we start out, consider the following situation where we have a function, right? And this could be a neural network, this could be a simple straight line, this could be any sort of function that takes some inputs and produces some outputs based on a set of parameters, right? So we've got our set of parameters W, and these are going to define this function's operation, right? Or some sort of output at least. Then we have some measure of how well this function performs, right? How well does it describe our data? How many errors does it make? Some sort of measure that says how good is this or how bad is it? And if we're looking at the error specifically, we can call this the loss. Our goal is to minimize that. Our goal is to reduce the errors that our function is making, or reduce the sort of badness of our function. We want to find some minimum there, right? So the question is how? How do we find some set of parameters that give the best possible result? And we've got a couple of simple options. We could just try all possible values or randomly guess, but those are going to hit limits real quickly, especially when you've got hundreds of different parameters, each of which could take on, thousands of different values. So we need some better approach. And so this is where gradient descent comes in, right? We are going to have some function or that produces some output. We're going to have a measure of the loss. So when you look at these graphs here, they're always some measure of the loss, and we're trying to minimize that. Okay, so our algorithm here, and we'll come back to this and reference it, so don't worry if it doesn't sink in straight away. We're going to start with some random parameters, and then we're going to say, okay, now for each of these parameters, what happens if I tweak them a little bit, right? More formally, what is the gradient of the loss with respect to this parameter? How does the loss change if I increase or decrease this parameter? And you can think of this as saying, like, which direction do I need to go to maximally increase or decrease the loss, right? This is the gradient of a slope. So again, if we look at all these examples here, we're finding the gradient, the direction of steepest ascent or steepest descent, and we're saying, since we want to minimize, if we know the gradient, we know which direction we might want to move to get towards the lowest point. Okay, so step one, start some random parameters, then find the gradient of the loss with respect to those parameters. And then if we know which direction reduces the loss the most, we can move a little bit in that direction, right? And so now we've changed our parameters. We've said this one needs to go up a bit, this one needs to go down a bit. So now I've got a new set of parameters. My function is producing a new output, and I've got a new loss. So I've updated them, and now I can say, okay, for these new parameters, right, go back to step two. Look at the gradient of the loss again at this new location. And then repeat this and repeat this and repeat this. So this is the gradient descent algorithm, right? We're going to do an example to try and understand this a bit better. But this is the core approach that's going to be used to iteratively, step by step, update our parameters to try and minimize some loss, right? So you can see, okay, we're already sort of vaguely starting to fill in some gaps of what we're doing here from this very verbose and intimidating definition. Okay, so let's start with an example problem, right? This is a classic. We have some data x and y with some sort of relationship between them. And you can see here I've just generated this data based on a function where the y is some number times x plus some offset plus some random noise, right? So there's some sort of relationship in this data here. So we've created this data, and we're going to try and find a function that, given an input x, is going to be able to predict our value y, right? In other words, something that's going to describe the relationship here in this data. So we've got our function, and you can see here it takes parameters. A and B are going to be our parameters, and we can use these to, by varying these parameters, we get different sort of lines, right? We get different functions, and they have different outputs. And so the next question is, okay, which of these is better? If you look at this, one of these does a better job than the other at describing the trend in this data. But how do we quantify this? We need some sort of concrete measure. And so there's several we could use. We could just look at how far away is each point on average from the line, right? Like a mean absolute error. Or we could use something, in this case, a very classic measure called the root mean squared error. Again, it sounds scary, but we're going to take the distance of each point from the line, the error. We're going to square it. We're going to take the mean of those squared errors, and then we're going to take the square root of that, right? So just following the name. And you can see the code is going to do exactly that. Y hat is going to be our predictions, in other words, the values that we get from our function. Y is going to be the true Y values. So we take the difference, in other words, the error, then we square it, then we take the mean, and then we take the square root, right? And there's many, many ways you could write this code. But this is just following the description and the formula. And then we can use this on our two examples above, right, these two lines. And we can get our function outputs right, using our parameters a and b for each line, and then we can compare them to the actual values and calculate the root mean squared error, or our loss, and we can see that the loss for the first one is much higher than the loss for the second one. And this makes sense. The error here is generally larger, so the squared error is going to be larger, so the average squared error is going to be larger, and so the root of that is also going to be larger. So we have some measure now where a lower loss means a better fit, right? So this is exactly what we want for gradient descent. We have some measure that can tell us how well we're doing. So time for a bit of an interactive demo. You're welcome to try this out yourself. We have our two parameters a and b, and in this case we can slide these around and see what happens. Oh, I need to actually run the code first. But once I do that, I can tweak this and see the line shift, right? What if we make this much lower? It shifts downwards. So this is our b parameter, and you can see the function up at the top there. So I'd encourage you to play around and keep an eye on your root mean squared error and see how low you can get this. And with a bit of tweaking, you can probably find, okay, we're getting significantly better now. But I also, while you do that, I'd like you to think about the process that you're taking when you're playing around with these sliders. Because maybe you're doing something like moving it a little bit and seeing, okay, if I move it in that direction, the loss goes down. Let me move it away even further. Oh, went too far. So you're tweaking back and forth and you're trying to find some sort of minima, right? You're trying to minimize this loss and get the best possible fit. So this is exactly what we want to do with gradient descent. Now, this sounds great, but there's one big question mark, which is, hang on, you keep talking about finding the gradient. How on earth do we do that, right? If you are someone who studied calculus, right, you've done lots of differentiation, you know how to find the partial derivatives of some function with respect to the different inputs. That's great. You can analytically, sort of mathematically calculate a formula for what the gradient should be. But that's not easy, and that's especially not easy when you get more and more complicated functions or chains of functions, and it becomes nearly impossible to manually analytically track that. Fortunately, PyTorch does some amazing magic behind the scenes. So what it does, every time we do an operation on something that requires gradients, right? So we have to specify of something we want PyTorch to keep track. But if we tell PyTorch, it'll keep track of the gradients, and then every operation that builds on that, it's going to add that to some sort of computational graph, right? It's going to keep an internal representation of what's happened, and also some representation of what it needs to find those gradients. So let's do a little example, and then we'll see this in action. So we're creating some tensor A, and we're telling PyTorch, keep track of gradients on anything that involves this tensor. Right, then we're applying an operation to that. We're creating a new tensor that is 5 times a plus 2. Then we're doing another operation on this new tensor, torch.sine, so just sinusoid function, 2 times b plus 0.1, and we get some output c, which is the result of these operations. But notice now it has this extra little thing here, this grad function, sine backwards. This tensor here knows how to find the gradient and move backwards to whatever its inputs were. So PyTorch is keeping track behind the scenes of everything it needs to be able to calculate the gradients. So that's really cool. How do we actually find those gradients? Well, if we would like to find the gradients of whatever our initial tensors were, of c with respect to whatever our initial tensors were, we can call c.backwards. And this is telling PyTorch, use the gradient functions and the computational graph that you've kept track of, and propagate those gradients back to find the gradients of c with respect to whatever the initial inputs were, right? And so once we do this, the A tensor now has a grad attribute, right? Our tensor A, remember, was just that 5.7 that we started with, but we can now access this gradient that's been populated once we called c.backwards, right? So if we say a.grad, we now have a gradient. And this is saying, how will c change if we tweak a? Now for this little example here, because it's fairly simple, you can get your formula for c based on a, you can plug that into Wolfram, or you can manually do it yourself, and you can find out that the formula for the gradient is this little equation here, And then we can plug in our value for a, which is 5.7. And when we look at the derivative of c with respect to a, we do indeed get this value, right? So PyTorch has done it correctly. And this is pretty magical because we can chain as many complex functions together as we want. And as long as everything is differentiable, as long as it's theoretically possible to calculate a gradient, PyTorch is going to be able to work backwards and give us all of those gradients. So this is super useful, and we'll see that in practice because it means that so long as our function is differentiable, we can do this gradient descent algorithm that we've been talking about. So let's go back to our example then. We have our function that takes some parameters. So now we're going to use two parameters, right, a and b, and we're just going to store those in a tensor. We're going to tell PyTorch to keep track of the gradients for those parameters. And then in a loop, because this is an iterative algorithm, we're going to find the gradients, well, we're going to find the loss, we're going to find the gradients using loss.backwards, and then we're going to update our parameters based on those gradients, right? And there's a couple of nuances that we'll come back and look at, but let's look through the code line by line. So we're creating our parameters. We need 2 for this function. We're telling PyTorch to keep track of the gradients. Then we're using an optimizer to do some things for us. And we'll come back and do this without the optimizer, but I'll explain the rationale for that later. Then some housekeeping. We're just going to store the losses so that we can see them later out of interest. This is not necessary. This is just useful for us to see what's happening. And then in our for loop, this is the key. And this is the kind of structure that you'll see again and again and again whenever you're training a deep learning model, whenever you're optimizing something. It's always going to follow the same sort of pattern. So we'll get really used to this over time. In a for loop, for some number of iterations, we're going to tell PyTorch to clear everything related to gradients, because by default it keeps track of them continuously. So saying, okay, forget all the history, we want to start a fresh calculation, zero all the gradients out, so that we have a clean slate. Then we're going to use our parameters to get our predictions, right? So this is now ax plus b, same as before. We're just using the parameters stored in our parameter tensor w. We're getting our outputs. We are calculating our loss using that same RMSE function that we looked at before. We're storing that for future reference, not important. We're printing updates if we need. And then the key here, loss.backwards, is saying, now that we found our loss, find the gradients that we need, backpropagate that loss through, and then this next line, a bit of magic, optimizer.step, is going to update the parameters based on the gradients, right? So this seems like it's just a little magical black box. Please excuse the birds. They always make noise whenever I'm doing a video. Yeah, so let's see what happens. Okay, we're printing out the loss. So we start out loss fairly high. After 20 iterations, it's dropped. After 30 or 40, it's dropped even further. And we can see on the graph, this gradually decreases over time until it sort of flattens out at some value here. Right, and now we can look at our parameters. Remember, we started these out randomly, but they've been continuously updated. And so now something close to 3, 0.05. We have our sort of learned parameters that are supposedly doing a good job. We can see the gradients because they're still, we're not perfect yet. The gradient is very small because we're quite close to optimum, but there is still some associated gradient. So if we tweaked the first parameter by minus a very, very small amount, we would expect the loss to increase by a small amount. I hope I got that right. Yeah, so we've learned these parameters, right? Over successive iterations, we've tweaked these parameters to get better and better and better. So we can look at what the graph looks like if we use these learned parameters, and we can see that looks like a really good fit. So this is great. We can also show the loss at different iterations, as well as the whole sort of loss landscape. So you can see here, this x is the first parameter and the y is the second parameter. We started out somewhere over here, and our loss was something like 1.9, right? And then every iteration, we tweaked our parameters some amount, and we've moved closer and closer and closer to some optimal value where the loss is really low, right? 0.3 or thereabouts. So this is really cool. We've managed to successively update our parameters to get better and better and better, right? Now there's a bit of magic. Optimizer.step, what is it doing? Well, it's not actually doing anything too crazy. And so, although I've introduced it for reasons we'll see later, we could do away with using PyTorch's built-in optimizer. It's not doing anything magic. So let's go back now to our loop and let's try and replace optimizer.step with us doing this manually, right? So remember, once we've said loss.backwards, we're going to have some gradient stored in w.grad. So we can use that gradient to see which direction would result in the highest increase. We want to move in the opposite direction, so that's why there's a minus sign here. We're saying we want to do the sharpest decrease, thank you very much. We want to minimize our loss. And then the learning rate, the step parameter that you might have seen it called, is saying, well, how far should we move in that direction? So this little 0.2 here is saying how far should we go in each update, because we don't want to update it too much. So let's try that. That's the same as this learning rate up here. So let's try with optimizer.step commented out. Let's try our own sort of custom little gradient descent update and see what happens. We get an error. So there's a bit of trickiness here, which is that PyTorch is constantly keeping track of all the operations and trying to keep track of how to go and find the gradients. So if we use W to update W, it's kind of like a little cycle that PyTorch doesn't really know how to handle. So it's going to say, hang on, I'm still trying to track the gradients here. I don't know how to deal with this. The fix for that is to say torch.nograd, because we've already done what we need from the gradient calculations. Oops. We've already found the gradients with respect to the loss. So when we called loss.backwards, w.grad has now been set to whatever the gradients is. So we can now use that, but we need to switch off all the gradient tracking to be able to update this parameter w with itself. So little extra nuance there to avoid that error. But with that one change, hopefully, this will work. And yeah, that looks exactly like we saw before. We start out at some fairly high loss. We get better and better and better over time. We can view our final parameters. They're not going to be exactly the same because we start from slightly different points, but they're pretty close. It still has some gradients attached. Once again, we can see the line and we can see the trajectory we took to get there, right? We started out here with these parameters. We got better and better and better over time. So this is great. Our gradient descent is doing what it said it would. It's helping us minimize this function iteratively over time. So if you go back to our definition, first order iterative optimization for finding a local minimum of a differentiable function, taking repeated steps in the opposite direction, right? This minus sign here, opposite direction of the gradient of the function, right? w.grad, and taking small steps, which is why there's that 0.2. Because this is the direction of steepest descent. So hopefully at this point you're starting to get a sense of, okay, I can see what's sort of going on here. And this little line here is basically all that's happening in optimizer.step. So although we can use the built-in optimizer, there's nothing too magical going on. And I wanted to highlight that. So this makes it seem like gradient descent is this beautiful, magical, perfect algorithm, and it is great. But there's a couple of nuances that we need to be aware of. One, it really depends on how large of a step we take, and that can have some pretty big implications. So for example, if we looked at the gradients and then we moved some long distance in that direction, right? So let's change the learning rate up to 2 here. You might think, oh, this means we'll get there even faster, but you can see our loss improves, but then it gets worse again, right? And if we go down running these cells and try and look at the trajectory that we took, what's happening is that we're looking at the gradients, we're taking a big step in that direction, and then now we're on the other side of this sort of valley, so we're taking a big step there, and we're kind of oscillating back and forth, and we're never actually getting to the optimum value. So that's not ideal. We could try a value that's even higher and see what happens to our loss now. Right, and now it's getting way worse, right? And we're just jumping all over the place. So clearly there's some situations where gradient descent doesn't cope so well. We need to make sure that we're taking fairly small steps. But if we tried something really small, it also is then going to take tons of time, right? Our loss is decreasing, but we haven't really gotten very far. So there's some reliance on that learning rate to say we would like to move such that we eventually end up at the minimum without taking forever. But we also don't want to move too far at any given step, otherwise we can overshoot or sort of get out of control and things can go really badly. So that's one bit of nuance. The other is that this particular function we're looking at is a beautiful, smooth, convex function. And that's not always the case. The loss landscape in many situations is much more ragged. There's lots of different local minima, and we're trying to find some sort of larger global minima. So there's lots and lots of cases where this algorithm isn't as perfect as we're making it out to be here. But it is still very powerful, and there's ways that we can address that, which we'll talk about in bonus section 2. Great. Okay. So hopefully that makes a bit of sense, right? We can go back to our definition and see now if we understand this. Gradient descent, iterative optimization algorithm, right? Step by step, trying to find some minimum, right? Trying to get the lowest possible loss or error. And the idea is that we're taking repeated steps in the opposite direction of the gradient, which we find thanks to PyTorch's automatic differentiation. And this is going to give us the direction to move that gives us the highest reduction in loss. So pretty nifty function. Hopefully now you've got a bit of an idea in your head. So yeah, with that, pause. I'm not going to have a one-sided ethics discussion now, but have a little think. We're choosing our error or our loss or our metric, and then we're using that to optimize some function. It's worth just thinking, especially if you're doing anything that's going to interact with people in the real world, what could be the consequences of choosing a specific target, a specific loss or metric, because that can have real world implications, and choosing the wrong metric can do some real damage. So anyway, whole big discussion there. There's some data ethics resources that we linked in the Discord, and I'll put them up in the resources channel as well. But anyway, little side note, pay attention, what are you optimizing for, and is that necessarily a good thing? Cool. Phew, that was a lot of stuff to get through. Thank you for bearing with me, and hopefully it's sort of starting to make sense. But you didn't think we were going to end without making some pretty pictures, right? This is an AI art course, so let's try now and bring this back and make some art with these ideas, right? How do we use all the tensor manipulations and stuff that we've done? How do we use gradient descent to get something out that looks visually appealing? So the demo we're going to do here, it's going to rely on this extra piece, which is the model Clip, right? Clip is a model built by OpenAI for connecting text and images. You can go have a read of their blog post or introductories or the paper. But the idea here is that they trained images with captions, and they trained this big model to be able to map both text and images into the same sort of space. So we're not going to look too deeply at it now. We'll talk about it later when we do learning representations and so on. For now, we're going to treat it kind of like a black box, and we're going to see how we can use this as part of our loss function. So this code here is going to download and install Clip, and actually I'm going to change my runtime type to GPU. This notebook runs fine on CPU, but it's a little bit faster on the GPU, and because I'll be doing lots of examples here, I'd rather just have it run quickly, so just going to run everything up to this point. And while we do that, let's talk a little bit about what's going on here. So we are trying to associate images and text, right? We're going to try and create an image to match some text. And so the way we do this, we are going to load the torch model, right, this perceptor, based on, in this case, a vision transformer. And this is going to be able to deal with both text and images as inputs. Just waiting for that to finish. There we go. So let's demonstrate that, right? We're going to give it some text, a watercolor painting of sunset over a mountain range. Excuse me. And this is going to take that text and it's going to map it to this embedding, right? This text embedding. And this is just a tensor. We can view it. This is a tensor of shape 1 by 512, right? And if we passed in a batch of texts, we would get some number of embeddings. But each one is 512 just numbers, right? So this is Clip's internal representation of that text. Okay, that's pretty cool on its own. What if we want to try an image? So here we're going to create an image, and we said batch size by channels, by width, by height, just making a random image in this case. Clip expects the images to be in some sort of range based on its training data. So we have a transforms.normalize that's going to sit in that process. But with that little tweak out the way, we can embed that image, right? Perceptor.encode image as opposed to encode text. And we're going to pass in our normalized image, and we get back an embedding. And interestingly, this is exactly the same shape as the text embedding. And when we look at it, it looks exactly the same. It's just 512 numbers that represent this image. So we have a representation of the image and of the text. And clip is designed such that if the images if an image and a piece of text go together, their embeddings, their representations will be fairly similar. Whereas if they're drastically different, then the representations are going to be different. But now we have some way of like comparing directly text and images. So we need a measure of how close they are. We could first of all try the root mean squared error or root mean squared difference, right? Since that's something we already did earlier in this notebook. So let's do that. We're going to get the embedding of the image. We're going to compare it to the embedding of the text. We're going to get the error. We're going to square it. We're going to get the mean. We're going to take the square root, right? Root mean squared error. And so we can use this loss function now to compare an image and our embedding of the text, right? And this is going to give us a result, 0.49 as our loss. So if we're looking back at our earlier gradient descent example, we're in the same sort of place, right? We have some parameters. In this case, the parameters are just going to be the raw pixel values of the image. And we have a way to measure our loss, right? This clip loss function that we've just written, which is going to compare our image with our prompt, our text. So can we use the same optimization loop as before and create an image? Well, let's see, right? We have our target text, right? A watercolor painting, you can tweak that to whatever you want. We have our image. We're telling PyTorch, hey, keep track of the gradients on this image. We're making a copy for later, doesn't matter. We're using the gradient descent optimizer. We're giving it a learning rate, quite a high learning rate, which we'll talk about. We're going to keep track of the losses. This TQDM is just a progress bar. For some number of iterations, we're going to zero our gradients. We're going to calculate our loss. We're going to call loss.backwards to calculate the gradients. And we're going to call optimizer.step, right? That's the core of this loop. Everything else is display or fluff. And if we do this, we can then see what our results are, and hopefully we get an image, right? That's the dream, that these raw pixels get tweaked more and more and more to resemble, oh, look at that, a beautiful sunset over the mountain range, right? Am I the only one who can see that? Just gorgeous. Well, not really, hey. So what's going wrong here? You can tweak the learning rate because that's one obvious sort of knob to turn, but you're never going to get a very good image out of this, and there's a couple of reasons. So one of them, let's look at the difference between the starting image and the finishing image, right? And let's see what the differences are. And you can see we get this weird sort of tiled pattern and these really sort of extreme differences. So a couple of things are happening. One, when we plot this, we see that it's having to clip the data to treat it like an image, because some of these parameters, some of these pixel values have gone above 1 or below 0, kind of out of the allowed range. They're kind of getting too extreme. So that's one issue. The second is that root mean squared error is great for the first example we saw, but it really falls down when you're trying to measure similarity in a really high dimensional space, right? And there's lots of interesting theory behind why that is. And if you look it up, you'll see people talking about, oh, you know, everything maps to the surface of a hypersphere, and it's really complicated. But the sort of takeaway is our loss function here is not the best, right? Raw like vector distance or root mean squared error, those aren't going to be good measures for similarity in a high dimensional space. We need something better, something like cosine similarity or great circle distance. So that's the second issue. Third, the clip model that we're using is a vision transformer which breaks the image into chunks called patches, right? And you can see in our difference image here, you can see that each patch is kind of operating separately. And so the pixels within that patch are just kind of like trying to maximize the output of that patch such that the final sort of loss is as good as it can be. But this is not ideal because we get these kind of artifacts from the fact that this is breaking it up into these smaller tiles. So that's not great either. And like I said, the learning rate is a little bit high. You can try tweaking that. But how do we fix this more generally? Well, one fix is to use a more appropriate loss function, right? In this case, the great circle distance squared. It's just a mathematical formula, a measure of how similar these 512 dimensional vectors are. So changing our loss function to something a bit better. But then the second tweak we're going to do is we're going to apply some transforms to our image before we feed it to clip. Right, so every time when we calculate the loss, instead of feeding the same exact image, so the same exact pixels hit the same exact patches, we're going to skew it a little bit, and zoom in a little bit, and blur it a little bit, and just shift it around and make it a little bit more interesting. And then finally, we're going to restrict the values to between 0 and 1 so that we don't get anything more extreme. Right? So I've done these tweaks, and I put them in this sort of neat little code cell here. You can click show code and take a look. In fact, let's actually let's hide the form for now. So I mentioned transforms. We're using Torch Vision's transforms here, so we can just stack together a random crop, a random affine, and sort of skew, shift the colors a little bit, add a little bit of blur. So this is going to help like vary things up and avoid us getting those tiling artifacts. And then in our loss here, we're going to get the embedding of the transformed version of the image. So this TFMs here is applying these transforms. That's all that's doing. So we're getting the image embedding, then we're normalizing both embeddings, and we're calculating some sort of mathematical function here to get our final loss. Right, so you don't have to worry too much. You can go look up the formula for great squared, great circle distance. But this is just our new and improved loss function. Right, so we're adding some transforms. We have a new formula for our sort of distance measure or similarity measure. Then the rest is going to be fairly similar. We have a watercolor painting, so our prompt is the same. Our image is the same. We're still tracking the gradients on it. We've got a slightly lower learning rate, same optimizer. Same number of iterations, same loop. It's all exactly the same apart from those two tweaks. And so if we run this, let's see if those changes made an appreciable difference. Hey, there we go. Now this really does start to look like a sunrise over some mountains. It's still not perfect, right? There's a lot more we could do, but it's a hang of a lot better than the garbled mess we saw before, right? If we look at this. So we've definitely made some improvement. Now these transforms, I kind of just picked them randomly from, if you Google Torch Vision transforms, you'll see the documentation. There's a whole bunch of options, right? Some of them flip the image, resize, shift around, crop in, etc. One big improvement we could make would be to say, well, instead of just calculating the loss on one random transform, why don't we do 8 different versions or 30 different versions of these transforms, calculate the losses for each of those and take the average. And what that's going to do is that's going to smooth out our loss function a little bit. It's not going to be so random, and it's just going to give us more variation and a better measure of the gradients so that we do better improvements. Yeah, so that's one option, is running multiple crops. Another would be to try and find other ways to improve this. But even as we stand, right, this is already kind of mind-blowing, because I hope it's mind-blowing, because we've taken this gradient descent approach, and we've said as long as we have a loss function that we can differentiate, and the whole of the clip model, this big complicated, right, like if we look at the perceptor here, this is a big PyTorch model, right, a big stack of neural network layers, all in a big complicated arrangement. But it's all differentiable. So if we have a loss function that's differentiable, and we have some parameters we want to optimize, then we can use gradient descent to tweak those parameters to improve our loss, right? To minimize our loss, or at least reduce it. And we can use that artistically. So I'd recommend, play around with some different prompts, change the number of iterations, change the learning rate, and see what you can get. There's some lovely results posted in the Discord for lesson 1. Please post yours there as well. I'd love to see how good you can get this. Cool, so that's the end of that bonus section. A few little housekeeping things before I forget. I promised an explanation of why we said we need quite a high learning rate here. And the intuition for this is simply that we have 224 times 224 times 3 parameters, right? So that's what, 120,000 parameters. And so each individual parameter is only going to affect a really small part of the output image. And so the gradient with respect to each little pixel is going to be some really tiny component of the larger gradient. And so that's why the learning rate here is going to be some large number like 50 or 100 versus a more usual learning rate that you would see in something like deep learning, which might be 0.01, right? So that's the reason for that discrepancy. We just have so many parameters and they all have a relatively tiny effect on the final output. Yeah, I also link in here some other notebooks that are based on very much the same approach. I wrote these a long time ago, or relatively long time ago. I haven't looked at them since, but given the tools that we've covered in today's lesson, you should be able to take these apart and sort of see what's going on. So the only difference between this and the example we've just done is instead of just optimizing a raw sort of set of pixels, we're going to represent an image as a stack of larger and larger mini images, right? So you can see here we have a low resolution image, then a higher, then higher, then highest. And by stacking these all together, we're going to get our final image. And this just means that we can tweak pixels in these earlier layers and have a much larger effect on the output. So it just means that things learn fairly fast, a little bit more smooth, and the outputs tend to be just generally nicer. So you're welcome to go play around with that, change the number of layers, look at what's going on under the hood. Yeah, nice little notebook. There's also a demo version where you can just, open it up. It's a single form, fill in the parameters that you want, hit go, and see what you can get. But if you do dig into the code, you'll see it's different code. The clip loss and transforms, somebody else wrote that code. So if we look up here, make cutouts is just taking several different crops of the image and feeding them all through clip so that you can get a smoother loss, like I said. They use a different library. They use cornea.augmentation for their transforms and flips and so on, whereas we just use the sort of, in my opinion, simpler, the torch vision transforms. But yeah, totally up to you which you prefer, but the hope is that you can kind of at least read these notebooks and understand what's going on. Okay, we're nearly there. I think I'm nearly at an hour of talking. But just finally, let me quickly just skim over this final section. So we mentioned that we're using gradient descent, and it has some issues, right? It takes a long time if your learning rate is too slow. It can get out of control if your learning rate is too high, and it has a couple of other little nuances. So it turns out there's been a lot of innovation in this space, right? And here's an excellent article by Seb Ruder, just looking at all of the improvements that have been made and all of the different algorithms that are available. But a lot of it comes down to saying, okay, we have this metaphor of like moving down a hill. Are there ways that we could improve this such that, maybe we're able to bounce out of tiny little local minima such that we can keep going down to some global maximum? Yeah, we could add in some idea like momentum, right? Some sort of physicality-based idea where we look at how far we moved in the previous step, what the gradients were there, and we use that to kind of like build up an idea of speed or momentum such that we sort of keep moving in some direction even if the local gradients point in a different direction. There's lots of work being done saying, well, what if we, instead of using a set learning rate and taking the same sort of step size each time, what if we did an adaptive learning rate, right? So RMS prop and Adam, we're going to take into account the previous gradients and the steps and the improvements and everything, and we're going to use that to calculate a learning rate rather than having just a single set value. We can also have different learning rates for different parameters. So lots and lots of great theory, lots and lots of great research being done. The nice thing for us, and this is the reason why I set us up using the built-in optimizer, is all of these are built into PyTorch, or at least many of them. So if we want to try a different optimizer, where before we had SGD, which is just stochastic gradient descent, in PyTorch we often don't put all the data through, we put it in batches. But if we put everything like we're currently doing, this does vanilla gradient descent, right? But if we change this to Adam or AdamW or RMS prop, any of the built-in optimizers, we can use those and see what happens. So it's really easy, single line change, and then we get to see what effect that has on our output. And because this is an adaptive method, right, we now are back to specifying a fairly low learning rate. And you can tweak this and see how it affects the speed at which the loss changes and the final image output. Right, that's looking different, and that's looking pretty cool. So that's one thing to note. With the built-in optimizers, you get all of these advanced sort of researched techniques for free. And then many of them also have additional bells and whistles. So we talked about regularization a little bit in the live lesson, but it's kind of a sidetrack for what we're doing. If you are interested, hit me up or have a search around and see if you can understand it. But the idea is that often, especially when training deep neural networks, we want to avoid any extreme values. We want to avoid any one parameter having too much of an effect on the final result. And so adding some sort of regularization, in this case, we're going to use the built-in regularization via the weight decay parameter. This is just adding a penalty. So instead of trying to just minimize our loss, we try and minimize some combination of our loss and some measure of how extreme our parameters are, right? And this helps kind of bring them back into a reasonable range and not have any one parameter skewing the output too much. So it's pretty nifty. You can play around with the parameters. You probably want to keep the weight decay fairly small since we want to focus on the loss and just have a slight reduction of anything that looks too extreme as far as our parameters go. But you can tweak those values and see what happens if we use a higher value for the weight decay, more harsh regularization. What does this do to our pixel values? Does it drive them to be sort of less extreme, closer to 0? We can see what the answer is with a bit of experimentation. Okay, yeah, so in this case, our image is now looking a little bit darker. Maybe that regularization is too harsh. So I'll leave that to you to experiment and to go Google if you're interested. Just, I guess, the point of this section is that we used our sort of basic gradient descent and it did decently, but there are more advanced methods, and the nice thing with PyTorch, they're all built in. And so if we would like to try something more advanced, we're sort of relatively empowered to do that. And you can know that behind the scenes, it's still doing something in this optimizer.step, which is looking at the gradients, right, which have been found here, looking at the gradients and then thinking, okay, how do I move to try and reduce the loss based on these gradients that I can observe? And the fancy optimizers keep track of the history and so on, but they're still doing that same thing. They're still doing an update. It's still this iterative optimization, and it's a really powerful tool. It's a really powerful tool for making art, and it's a really powerful tool for many, many other things. So I hope that was useful. We packed quite a lot in. Congratulations if you've made it through, and thank you for coming along on this journey. I'm really looking forward to the future lessons where we'll put these into practice in some different situations, right? We're going to see an optimization loop like this many, many times in different contexts, and hopefully you'll start to build this idea that, hey, if I can parameterize something, right, if I can generate an image from a set of numbers, then I can make a loss, and maybe that loss is via clip, maybe that loss is, does its style resemble some style image, does its content resemble another image? If I can try and minimize that, do I get a better image? If so, hey, I can use gradient descent to tweak those parameters and improve my image output, or whatever output it is. So it's a really powerful tool, a really fun tool to play around with. And hopefully now, if you take this learning and you go back and look at other people's notebooks that have been shared around, you'll see it's that same sort of pattern. Somewhere in there, they're doing exactly this, right? Some number of iterations, they're zeroing gradients out, they're finding a loss, they're lost up backwards, optimizer.step. You'll see this pattern hidden within the much more complicated and verbose code that's out there. Great. All right. Thank you so much. If you do have questions on anything I've said, feel free to message me or put them in the Lesson 1 channel on Discord. And yeah, we'll see you either next Sunday for the next live lesson, or if you're working through in your own pace, the notebook for that should go up in the next few days. And then once we do the lesson on Sunday, there'll be a recording from that that'll go up just like this one is today. Thank you so much, and I'll see you in the next one.